Hello everyone, my name is Björn. I work for a company called Grafana Labs and I've done one or two things for the Prometheus project. My favorite topic in the Prometheus world is histograms, or at least one of my favorite topics, and it's actually such a favorite topic that I have given more talks about it than just this one, and I decided to arrange them in a trilogy. And like we know it from popular movie franchises, those trilogies don't necessarily appear in the right order. So the logically first talk that you should watch first is this one, which I gave earlier this year at FOSDEM in Brussels. And that's about all the ancient history of Prometheus histograms. Very important to know and to understand why we are where we are now. The second part of the trilogy happened first, was screened first last year in Munich at PromCon, and this is kind of the centerpiece. It was supposed to be kind of a trilogy of its own with past, present, and future, but of course there wasn't enough time, so I decided to cut out the past, which gave me a reason to give this first part later. So this is a very important talk. You should totally watch it if you haven't. This is about what Prometheus histograms can do well right now and what doesn't work that well, and what are options to address that in the future. Now this third part of the trilogy, which is now, this is about actual things I tried out, and I followed a certain idea. And now I want to tell you about the results. This is all planned to be in a big and fat design doc or RFC that I'll send out very soon. And then the community can discuss and we can see what of my ideas we can actually implement in Prometheus and have better histograms. All right. One thing has already been improved, and I wanted to mention that first because that was raised in the second part of the trilogy as a problem. That's isolation. Prometheus is kind of almost acid, the TSDB part of Prometheus, but it was lacking this isolation aspect. And histograms were a favorite victim of that. In Prometheus 2.17.0, we finally got this implemented. Just one tiny line in the changelog, but huge step, support isolation. There is a lot of detail to share about this, which I don't have time for here, so I have to refer you to this awesome blog post written by myself, shameless plug, on the tech blog of my employer, another shameless blog. But here's the URL, just look it up and you see histogram quantile. That's the infamous function that gets hit quite often by the lack of isolation. We have isolation now, it's all good, you don't even have to think about it, it will just magically work. So let's come to the remaining problem of histograms, or let's first recap what are actually the things that work well. This is a slide, kind of flashback to the slide of the second talk, to one of the slides in the second talk. These are things that work well. Updex, score calculation, high frequency sampling is mathematically correct, which is actually you can't take for granted, unfortunately. And questions like those percentage questions. What percentage of requests in the last hour got a response in 100 milliseconds or less? These work really well, but unfortunately they only work well under circumstances. This is why all those, or most of these things, get a little asterisk. And as you know, this is usually where you read down here, terms and conditions apply, and then you know the deal is actually not as good as it sounded first. And with Prometheus histogram, you get this if suitable buckets defined, which is actually hard to define suitable buckets. There's this other thing, histogram quantile, which is what histograms were actually added for, to Prometheus to calculate quantiles like a median or 99th percentile in a correct way across distributed systems. And this is, it all works fine. It just has a few issues. Again, this is just recapping from the second talk. The accuracy depends on the bucket layout. And now we come again to bucket layout. Buckets are just super expensive. with the current Prometheus histogram. So you only can have a few of them, and then you have to pick them really wisely. So you need your interesting results you get here. They should be close to a bucket boundary. So in some areas of the observation range, you can have high resolution buckets, but not everywhere. Or you can't really have high resolution at all. Yeah, but then on the other hand, the bucketing scheme must be compatible across the aggregated metrics and across the range of rate calculations, which means you should actually not change the bucket layout, but since it's so hard to find the right one, you are actually tempted to change that quite often. So it's a kind of dilemma, and it's really annoying. Back then in talk 2, there was lack of ingestion isolation as a problem stated on this slide. I scratched this because, as I told you, isolation now just works. Okay, but we still have plenty of remaining problems. This illustrates the cost problem again with a different consequence. So here we have a histogram as you can configure it in Go code if you instrument Go code with the Prometheus histogram. So this has kind of 10-ish buckets. It's a duration histogram for essentially HTTP latencies. And then there is also a counter, which you shouldn't need because you're already implicitly counting requests in this histogram. But often you just have a counter, and you do this because this counter is partitioned by status code or path or method or whatever you want it to be partitioned by. You don't do this with the histogram because the histogram is essentially as expensive as a counter per bucket. So that's an order of magnitude more expensive than the counter up here. So you're really, yeah, you really don't want to partition this by too many dimensions. So that's a very common topic, a counter that is partitioned at will, and a histogram that's not partitioned at all, which is annoying because sometimes you actually want that partitioning, and you definitely don't want to think about this in the beginning. You want to ask those questions later when you look at your metrics. So let's formulate a wish list for the rest of this talk, what we want to accomplish. First of all, we are like spoiled kids here. We want everything that works well to continue to work well, of course, right? Second, we never want to configure buckets again because that's just annoying. But third, all histograms should always be aggregatable with each other across time and space. I never want to have this problem again. And of course, I want accurate quantile and percentage estimations across the whole range of observations. I don't want to have this area where, oh no, sorry, you didn't put buckets there, so you can't have good values here. But of course, fifth, I want all of that at a lower cost than current histograms, so that I can finally partition histograms at will. So, as said, greedy small kid, we want everything. Let's see how far we can get here. In the second talk, I have already hinted at the solution. That is most likely the solution to go for, which is essentially a very old approach. It's just have a conventional histogram. It just has infinite amount of buckets in a regular, usually exponential or logarithmic bucketing schema. But of course, the question is, how can you deal with an infinite amount of buckets? And the basic idea here is that you just account for buckets that actually contain at least one observation, and all the empty buckets are ignored. There are different approaches. There are certainly many more than this. This is probably the top 3 most well known, but perhaps not. HDR histogram, you have heard about it. Synchronous has an implementation which they have on the client part. There's open source code, and they have written a paper quite recently about it, but the approach is fairly old. And Datadog is probably also doing this for a while, but they have recently also published a paper where they explain their histograms. I should show you the whole link here, not covered with my face. Yeah, so here you can see all of that. The question is, if this is all so well established and old, why haven't we done this in Prometheus in the first place? And yeah, there are a few problems because Prometheus is a bit different. Let's first check out how this histogram, those sparse histogram as I call it, is usually done. You have this running on different instances. This is just one instance that is accumulating observations in a histogram, let's say for a minute. And of course, every instance is doing that. And then kind of at some point in time, they all send these histogram data to a central data storage where it's collected, and with some magic efficiency, will actually be able to save that, store that nicely. But for the monitor target, it's quite easy to then reset everything. So you have completely empty slate and you start again to collect observations. These histograms should all look slightly different. I was just too lazy to modify them a bit. So this means every minute you kind of start over. You start from an empty slate. You have zero entropy. All the buckets are empty. And then you only have to count for buckets that receive an observation in that minute. Then you ship it all over and you're done with it. So in Prometheus, that's kind of, unfortunately, very different. Prometheus is, as you have probably heard, a pull-based monitoring system, and many people complain about that. But there are a bunch of advantages, and this talk should not be about the advantages of a pull-based data collection. But I mean, Prometheus is doing that, right? This is not going to change, and we have to deal with it. And with Sparse histogram, we have the problem that for Prometheus, where scrapes are stateless, essentially, you cannot just reset at will and then decide to send the new histogram. You essentially have to accumulate data forever. And it's also nothing about like minutely. Any time somebody could come along and scrape, which is one of the advantages, but also difficult to deal with. So in Prometheus, this is accumulating, as I try to draw here, but you can probably guess what I mean here. So you get you accumulate a lot of entropy, more and more buckets are populated, and your histograms on the monitor target will take more and more storage space, which is a problem, right? So this is kind of where we were and where we said doesn't even apply to Prometheus. We just can't do that. But then also studying all the other alternatives as laid out in the second talk and realizing they also don't work, I started to think perhaps this works after all. And there is essentially a two-part thinking process here. The one is about the accumulating entropy. So this is essentially how many buckets you populate if you accumulate data for a minute. And then your chiplet would go back to zero and do more or less the same again, right? But if you just do it for 2 minutes, it's not that you have twice as many buckets populated, because more and more often you will hit a bucket that already has seen an observation. So at some point, this is the time axis here, at some point in time, you will reach some saturation level, where most of the time you will hit a bucket that has already some counts in it. So this is the idea that the idea is that you will approach this saturation value quite quickly, so that it's not that much of a deal if you collect for 1 minute, 2 minutes, 3 minutes, an hour, or a day. That's the one idea, right? The other idea is that in principle, Prometheus has a concept of resetting counters. It just doesn't have to happen too often. It will happen if you restart your binary, right? So Prometheus loses some counts if that happens, because as I said, it's pool-based. So a monitor target cannot just decide, before I die, I will ship all the metrics. It will just die, right? It will just go down. And you scrape quite often, like let's say every 15 seconds. So you might lose a few seconds of count. So if you now reset your histograms, let's say every hour, that's in relative terms not a lot of loss. So these are the two thoughts, right? First, entropy will not accumulate into infinity essentially. And second, if it does, I can still reset a histogram, let's say after an hour or so. So perhaps it works, and we have to study that. Another thing that Prometheus is doing in its existing histogram is this cumulative nature, which has a lot of advantages for like an operational quality of life aspect. You can like drop buckets from it if you want to reduce the isolation, the resolution, stuff like that. There are a bunch of things to say about cumulative histogram, but cumulative histograms really don't play well with the sparse nature of sparse histograms. So this is really something we need to change for sparse high resolution histograms. We just have to go to ordinary histograms. but that's perhaps something we can do. It's not as fundamental to Prometheus as this pull-based approach. All right, so this is how a sparse histogram looks like, very much simplified. You can represent them in different ways. This is the one I chose for an experiment. The idea here is that you specify the resolution of the histogram by saying how many buckets there are for every power of 10. In this little picture, I used 3 because I didn't want to draw hundreds of buckets. In practice, this will be somewhere between 20 and 100. 100 will be super high resolution and 20 will be an okay resolution. I just had 3 here. The buckets are all logarithmic, which you can't see here because the x-axis is already logarithmic, right? So I did it that way because otherwise the buckets would be super tiny here and super big here. So they look linear, but they are logarithmic because the axis is logarithmic. You need a 0 bucket because with logarithmic buckets you will have an infinite bucket density if you approach 0, and you might just have observations that are 0 or very, very small. So you define a 0 bucket, which usually has a width that is super, super small. In this case, I picked 0.1 just that I'm able to draw it. And here we have 3 buckets. Then there's an empty bucket. It's a sparse histogram. And then there are 3 other buckets, and you can continue this into infinity. So how does this all work in real life? To test that, I took observations from a real production cluster here at Grafana Labs from our Cortex cluster. If you know Cortex, you know what ingester and query means, but we don't have to worry about that. The only important information is that the query has a very broad distribution of latencies, durations. So this is like a high entropy scenario, while the ingester is more like it has a smaller distribution. Most of the requests the ingester processes are processed in more or less the same duration. So I collected the ginormous amount of almost 2 million observations here and a bit more than 500,000 for the querier, and put them all into one histogram. That's kind of a worst case scenario. In practice, you would probably have a histogram along certain dimensions and you would have it on every instance. This is really like to brute force test it, put all the observations into one histogram. By the way, the 2 million here are happening in just 2 minutes because it's a super busy cluster. The querier is not as busy, so those 500,000 was over an hour. So resolution 20 buckets per power of 10. In fact, with this ginormous histogram, only 78 buckets were populated. With this less observations but higher entropy distribution, 112 buckets were populated, a bit more. The span here means how many continuous spans of subsequent histograms there are, right? So this means there are 2 groups of buckets. Sorry, did I say histograms? Buckets. Spans of buckets, right? So there are 2 groups of buckets and there is at least an empty bucket in between. And here all the 112 buckets are actually in a row, right? There's no empty bucket in between. You can also go to much higher resolutions. So this is the higher end resolution of 100. We have many more buckets and also more spans. Like more often you have some empty buckets in the middle. But overall, like a couple of 100 buckets, I think this is something we can manage. So this gave me some confidence that I'm on the right track. So what I did next, I thought about how to encode these histograms and represent them first of all in the exposition format, and how to then encode them in the TSTB. Of course, a lot has been thought about this. This is just, I had to come up with something to try it out in the Prometheus context. So there's a 0 bucket, and then I number the bucket. I start with 0 at the bucket that has an upper bound of 1. And then I go negative to the left and positive to the right. This bucket doesn't exist, but it still has a number. And then those are organized in spans, as we have seen, spans of consecutive buckets. This is a span that starts at bucket number -2 and has a length of 3. And then we have a gap of 1. So the next span has an offset of 1 and a length of 3, and so on. So these are small numbers then, and you need very few, very small numbers to describe the whole bucket layout. which is great. Because small numbers are nicely, they encode quite nicely with a var_int encoding scheme, which is essentially built into a protobuf, which simplifies things a lot. The other thing are, of course, the counts in the buckets. They tend to be really high, like we have seen. There are millions of observations in my data set. So you don't want to encode the absolute numbers, but since a histogram is usually like smooth in some way, goes up and down, but not zigzagging like crazy, this is why I encode deltas from one bucket to the next. They are usually small, can be encoded with var_int quite nicely. And I skip over gaps, just take the delta here, and this is how it works. If you put this into a protobuf and you have a proto-based exposition format, which was, by the way, what Prometheus used in the beginning, and only the current Prometheus server uses a text-based format. We'll talk about that in a minute. So if you put this all into a protobuf with using var_int and specifying those spans and deltas nicely, this is what you get. This 78 bucket histogram takes 244 bytes. The slightly larger takes a bit more. And even if you go to a really high resolution, you have more buckets. What is really nice that this is essentially 5 times the resolution, but the size on the wire is significantly less than 5 times, right? So you gets more efficient here with more buckets. So is this a lot or not, a kilobyte? We can look at how it looks in the current text format that we use for histograms, and it looks fairly repetitive. So this is a very simple kind of 10-ish buckets histogram, and this one takes 1.6 kilobyte, as you see it here. These are 1.6 kilobytes, right? There's also this older protobuf format, which is more condensed, less repetitive, but even there, as you can see, 300 something bytes for like 12 buckets, while here we have kind of the same number of bytes for 100 buckets. So clearly we're doing something right here, right? The exposition format as sketched out here works. Okay, so exposition, let's say we can handle that, right? Now storage. This is also interesting. How do we store this? The basic idea that should save us a lot is that we need to just save one time series per histogram, not per bucket. That's what we do right now. That was decided back then just out of simplicity to not change Prometheus completely when you introduced histograms. Every bucket is its own time series, which has huge overheads, as you can see. Also because like cardinality is that the bottleneck currency in a metrics-based monitoring system. So now we kind of say we can have a lot of buckets, but it will still be one series per histogram. But that means a sample value is now a sequence of buckets instead of a float. And we can take the bucket deltas to have smaller numbers. And those values, why not? We can encode them in the same way we already encode timestamps, which is a double delta encoding. So I call it triple delta because we double delta encode a bucket delta, right? It sounds fancy. And then those are encoded with a what we call var_bit schema. That's Gorilla style. It's a bit different in detail, but mostly what you probably know from the Gorilla paper. It's again used for timestamps already, and we can use it for those triple deltas. So if we do this, we can see how much storage we need for those triple deltas. This completely ignores how to handle like bucket layout and schema changes and everything. It's really just to get the bulk storage nailed down and to find out how much space it needs. I didn't implement a whole TSUB. I really just simulated scrapes, 80 scrapes for the ingester dataset, 240 for the courier, and found out what triple delta we have here. And then we see a histogram will take 50 bytes. Now, not on the exposition format, but in the storage where we want it to be like compressed over time in the time series. So every histogram takes 50 bytes here, 70 bytes for the higher entropy case. And in the high resolution case, it takes more, but again, far less than a factor of 5. And if you break this down to bytes used per bucket per sample, then you come up with a fraction of a byte here, like 0.5 more or less. Now, as you might know, in vanilla Prometheus for normal floating point value samples, we need like about 1.5 bytes per sample per floating point number, which is 3x. Now this is already kind of the worst case scenario here, so we might be at 5x or something, or even a bit better, but we also have probably 10x the amount of buckets compared to conventional histograms. So overall, the storage space will probably be a bit more demanding, but on the other hand, we will save a lot with the index. So that overall should hopefully, this is what I hope for, we should be more or compare, like more or less the same efficiency or better. Querying, that's a big deal because I haven't done concrete research about this, because then you really need to implement the TSDB, and then you have to teach PromQL how it can deal with like those complex histograms instead of just individual buckets. But I have good hope that this will actually work out nicely, because others have done this. It's like more than just one group of people has done this, but I have to pick one, right? And I really liked this talk at Monitorama last year about PhyloDB. Evan Chan gave this, and slide 23 is my favorite. I mean, the whole talk is great because it very nicely explains all the problems with Prometheus histograms and what you can do about it. And slide 23 is showing that histogram quantile calculation is 100 times more efficient in PhyloDB, where they use approaches quite similar to what I'm planning here. So this is what gives me hope that it will just work. Okay, let's quickly go through our wish list and see how this will work out. Everything that works well now should continue to work well. This is mostly true. Spoiler, most of the answers here are almost. So the one thing that works really well, if you have like an SLO, which reads like 99% of queries to be served in 150 milliseconds or less, then you can just put a bucket boundary at 150 milliseconds and you have a precise answer from Prometheus. And now with the logarithmic histograms, it's just impossible to get a boundary at 150 milliseconds, but you have like boundaries very close to that, so it's almost there, right? This is the only thing that works in principle a bit less well. I never want to configure buckets again. I told you there are just two parameters, the resolution and the zero threshold. This is real Go code from my proof of concept code. Now in practice, you will never configure the zero threshold. It would just be at this very small value and you never have to change it. And ideally, we will find a resolution that is good enough for everyone, but not too high to not be too expensive. And you never have to touch this either. It could be 42. That would be fun. It will be somewhere between 20 and 100, 200. I'm pretty sure about that. And yeah, we just have to find something, right? Because if you change this resolution, you run into the next problem. All histograms should always be aggregatable with each other across time and space. Yeah, if you change the resolution, you will not have this, but ideally there's a resolution that will cover most of the cases, and only in very special cases you have to change that. I want accurate quantile and percentage estimation across the whole range of observations. It's also almost, I mean, quantile calculations are fairly accurate with a resolution of 100. You have like about 1% of worst case relative error, which is fairly good compared to like the industry, what they're all doing. A percentage has this one problem that you cannot really pick where a bucket boundary is, so you have some tiny error there. But overall, from my research results, I'm very satisfied about this one. I want all of that at lower cost than current histograms so that I can finally partition histograms at will. This is orange because I really can't tell if it will really be dramatically lower in cost. I'm hopeful that it will, all of this awesomeness will be same price essentially, or lower, hopefully lower, but we have to see. All right, this now we are at the end. You can look at all those rough results in this GitHub repo. It's very rough, really. It's just my experience repo. The code has horrible quality. I just wanted to try things out. I'm writing a proper design note, which I will shortly announce on this mailing list. So follow this and you can pick it up when it's there to be reviewed by the world. These are my talks. This is my email. But this leads us to the end. So we have 5 minutes and 5 seconds left for Q&A. Thanks for your attention and see you in the Q&A. Bye bye.